Hi, everyone, and welcome back to Psych 3510. Today, in this video, we will be discussing hypothesis testing with bivariate correlations. This is going to be part 3, sort of an extension of chapter 8. You already have 2 videos, part 1 and part 2, that go into what are bivariate correlations, how do we describe them, and then how can we interrogate them. This part 3 moves a little bit beyond the textbook and is going to apply this idea of hypothesis testing to bivariate correlation statistical analyses. So this lecture is going to be all about how we calculate a bivariate correlation by hand, and then how we make a hypothesis testing decision about whether to reject or fail to reject the null, how we write up an APA-style conclusion, and then express our sort of take-home message about our association claim, our research question, to our readers. So let's dive right into what the formula for a bivariate correlation looks like. It looks big and scary. Don't worry about that. We're going to break it down. We actually have 2 formulas here. We have the formula for R, which is our correlation coefficient, our test statistic for a correlation, over here on the left. And then we're going to need a second formula that we already are familiar with, our Z-score formula. This Z-score formula is going to help us build to our correlation coefficient R formula. So we're going to need to use both of these. We're familiar with the one on the right. So let's break down a little bit the formula on the left, and then we're going to do some examples and walk through step by step. So our correlation coefficient, we denote with a lowercase r. You'll often see it italicized. Sometimes you won't see it italicized. Basically the same thing. R is our correlation test statistic. The numerator of our formula is the sum of, right? This is sigma, and in math, this means the sum of the Z-score of an individual's variable X times the Z-score of that same individual's variable Y. So remember, our research designs for a correlation is one in which we want to understand the relationship between variable 1 and variable 2, or here, variable X and variable Y. And we want to understand how these 2 variables sort of move with each other. Do they move together in a positive correlation? Do they move in opposite directions in an inverse or a negative correlation? Or is there no relationship between these 2 variables? So our old friend, the Z-score, is really valuable here, because if we really think about what a Z-score does, a Z-score says, how far is an individual X from the mean based on the standard deviation of that variable? Are you below the mean but very close to the mean? Are you below the mean but very far away from the mean? That would be a negative Z-score. Are you above the mean but very close to the mean, meaning a small positive Z-score? Or are you greater than the mean and very far, very extreme from the mean? That would be a large positive Z-score, right? So our numerator is distance from the mean divided by the amount of variability we can expect in that variable, standard deviation. So a Z-score tells us in what direction a score is moving relative to its mean, and how extreme a score is relative to its mean. And so if we have a single individual and we have their Z-score for variable X and we have their Z-score for variable Y, then we can assess the relationship between those 2 variables. So in a positive correlation, if I'm below the mean on variable X, so I have a negative Z-score, I should be below the mean on variable Y, another negative Z-score, right? They're both negative, which means I'm below the mean on both, which means they sort of move together. Similarly, for a positive correlation, both Z-scores for the same individual on our 2 variables might be positive, right? So if I'm above the mean then I have a positive z-score on both variables, meaning they also move together. So in a positive correlation, we will tend to see individuals whose z-scores have the same sign. They're either both negative or they're both positive because they go together. In a negative correlation, we will tend to see individuals with z-scores of opposite signs, meaning I'm maybe very high on X, very high above the mean, but I'm very low on Y. I'm very far below the mean, meaning they're moving in an inverse relationship, opposite directions. So what this formula tells us to do is take every individual, calculate their z-score for variable X, times that individual's z-score for variable Y. We get sort of a z product, if you will. I think that's what we're going to call it. We get a z product for each individual. We then add up all those z products, right? That's what this sigma means. And then we divide that summation of z products by n minus 1, where n is equal to the number of pairs of scores, or basically the number of individuals, the number of people in our data set, minus 1. So this is all very probably difficult to understand just looking at the formula. So what we're going to do is just dive right into a step-by-step example to see how these two formulas work together to produce our correlation coefficient. Okay, here's a full overview of the math that we're going to do all the way through from what we might call our raw data, just an individual's scores on our two variables, all the way to, down here in the bottom right, our correlation coefficient. So you can refer back to this slide to get sort of a bird's eye view of the calculations, but what we're going to do next is take them step by step so that we're comfortable with them. I want to orient you to the research question here. I think it's an example actually pulled from part 2 of this lecture, where we're looking at participants' height in centimeters at age 2 being correlated with their height in centimeters as adults. So essentially, are tall 2-year-olds tall adults? Are short 2-year-olds short adults? Is there no relationship between height at 2 and adult height? Or is there an inverse relationship? Do tall 2-year-olds become short adults, right? We don't know, but we have data from 7 people. For each participant, we have their height in centimeters at age 2, and we have their height in centimeters as an adult. So these are what we call our raw data. It's just the scores from our individuals. And we're going to look at what happens when we just start from raw data, how we can get all the way to an R. One very important point that I cannot stress enough when doing these calculations is that our signs, whether a value is positive or negative, is unbelievably important. It's generally important, right? Obviously in mathematics. I guess I want to say it's particularly important when calculating in a correlation coefficient. If you remember back to some of our other calculations, like our t-test or our sum of squares, we end up squaring values in those calculations. And so all of our negative signs become positive and the signs go away. In this case, the signs will not go away. We want to pay careful attention to whether a value is positive or whether a value is negative. And we want to hold that sign with that value as long as it is mathematically needed. So be very careful about your signs. Also, remember, we are rounding everything, every single calculation we do, to 2 decimal points, right? To our 100th place. So step number 1, given raw data on the height of individuals at age 2 and the height of individuals as adults, is we need to find the mean and the standard deviation of each variable. So we're not going to go over how to do that because you should be comfortable given the last few sections of this class, taking a list of scores, right, averaging them, and then completing your sum of squares table to find a standard deviation. We want to go from mean to deviation score from the mean to square deviation to the sum of those deviations. We then find a variance, and then we use that variance to find a standard deviation. Now, excuse me. Looking forward to what you'll be expected to do for this class, I'm actually going to be pretty nice, and I'm going to give you not only the raw data when you have to do these examples, but I'm just going to give you the mean and the standard deviations as well to save us some time. We're going to assume, hopefully, that you know how to complete these calculations already that we've gone over this semester. So if you're unsure of what we mean by standard deviation or where it comes from, go back in the course and look that up and familiarize yourself. But for correlation coefficients, I'm going to give you these values, the means and standard deviations for each variable. So we can see that for height in centimeters at age 2, the average height is 83.28 centimeters with a standard deviation of 5.28. The average adult height in centimeters is 165.29 with a standard deviation of 8.16. Step 2 is to calculate the z-score for each person on whatever this first variable is. So we need our z-score formula. Z equals each individual score minus its mean divided by its standard deviation. We have everything we need here for variable 1. We have all our individual scores. These are our x's. We have our mean 83.28, and we have our SD 5.28. So we just plug and chug to generate these values, the z-scores for variable 1. So here, for participant 1, we're going to take 78 and put that as our x. We're going to take that variable mean, 83.28, put it as our m. We're going to take our variable 1 standard deviation, 5.28, put it as our denominator down here. We get 78 minus 83.28 divided by 5.28 to give me a z-score of negative 1.00 for participant 1, variable 1. Notice this person was below the average height as a 2-year-old, right? The average height was 83.28 centimeters. They were 78 centimeters tall as a 2-year-old. So they're below the average. And so that's why we get this negative 1, this negative sign. This negative sign is crucial because the point of a correlation is to understand if you're high on one variable, are you high or low on the other variable, right? If you're low on one variable, are you high or low on the other variable? So we need to know the relationship of each person to the mean. And in a z-score, the sign tells us that. If you have a negative sign, you're below the mean. If you have a positive sign, you're above the mean. So we plug and chug for person 1, variable 1, and we get negative 1.0. We could plug and chug for person 2, variable 2. We take their score of 80. We plug it in for x. We take the mean of the variable, plug it in for m. We take the standard deviation of the variable. We plug it in our denominator. 80 minus 83.28 divided by 5.28 gives us a z-score of negative 6.2. And we can see this person was also shorter than average, right, at 2 years of age, but less extremely so, right? They were, we might say, less short than person 1, right? Person 1 was 78 centimeters. Person 2 is 80 centimeters. Person 1 is more extremely short, so they have a more negative z-score of 1.00. Person 2 is less extremely short, so they have a negative z-score of 0.62. So we're going to do the same thing for each participant for their variable 1 scores. Just plug and chug, and your variable 1 scores put into our z-score formula turn into the z-scores you see over here in the middle of the screen. So we can see person 1 is pretty extremely low, or maybe relatively extremely low on height at age 2. Person 2 was closer to the mean, but still kind of below, but still short, still below the mean. Person 3 was a very tall 2-year-old. Person 4 is very close to the mean. They're basically an average 2-year-old. Person 5 is, again, kind of a short 2-year-old. Person 6 is a very tall 2-year-old. And person 7 is a moderately short 2-year-old. Negative 0.43 standard deviations below the mean. We can do the same thing for variable 2. We take each individual, we plug their score in as x, we plug the mean, 165.29, in as our m, our mean, and we divide by that variable standard deviation, 8.16. And so then this tells us how extreme above or below the mean every individual is on variable 2, which is adult height in centimeters. So I want us to take a quick look at maybe eyeballing the relationship between these two variables. So person 1 was short as a 2-year-old, and they're even shorter as an adult, right? Negative 1.88. Person 2 was kind of short as a 2-year-old, and they're kind of short as an adult. So these two people, their scores on variable 1 and 2 go together, right? They have the same sign. They're both negative. What this means, perhaps counterintuitively a little bit, is that they are contributing to a positive correlation. Because remember, positive correlation, the positive doesn't mean big or little, right? The positive doesn't mean greater than. Positive means goes together. The two variables move in the same direction for individuals. And that's what we see here. If you were a short 2-year-old, you were a short adult. If you're a short 2-year-old, you're a short adult. Person 3 was a tall 2-year-old, and they're a fairly tall adult. Not extremely tall, but somewhat tall. Person number 4 was a very average 2-year-old, and they're a pretty average adults. Person number 5 was a short 2-year-old, and they're an average adult. Person 6 is a tall 2-year-old and a tall adult. Person 7 is actually contributing to an inverse relationship, right? They surprised us. They were a small 2-year-old that became a kind of tall adult, or a slightly above average adult. In general, the z-scores go together. If you're low on one, you're low on the other. If you're high on one, you're high on the other. So this is looking like a positive correlation to me, because the values are moving together. Now, this is the most time-consuming part of our calculations, getting the z-scores. We have to do, if we have 7 participants, we have to calculate 14 z-scores, right? This is the most time-consuming part. Get comfortable with doing this calculation over and over and over again accurately. Make sure that you have the correct order in the numerator. X always comes first, the individual score minus the mean. That way, the sign tells us whether they are above or below the mean. Do not, I repeat, do not put M first and X second. It matters. So get comfortable with this, because if you can do this accurately and quickly, then the rest of our calculations are pretty straightforward, because step 4, our next step, is to find our z products. So we take each person's 2 z-scores and we multiply them together. So -1 times -1.88 produces a positive 1.88, right? 2 negatives multiplied together gives me a positive. We do that for each individual. We just multiply across, multiply across, multiply across. And I want us to quickly notice something here, that when variables move together, so when we have 2 negatives, they produce a positive number. Person number 2, the variables move together, they have a negative, they produce a positive number. Also, when we have 2 positive z-scores, right, they're still moving together, So we have another positive number. So what's happening here is that as our two variables move together, whether that's up or above or below the mean, they're producing positive z products because they're going to generate a positive correlation coefficient, because a positive correlation is one in which the variables move together. So if they move together negatively, they still produce a positive z product. If they move together positively, like person 3, they produce a positive z product. If we look all the way down here at person 7, their z-scores move against each other, right? They're below the mean on one z-score and above the mean on the other z-score, which leads to a negative z product. They're going to contribute to making the R coefficient negative, right? They're pulling the R coefficient in the opposite direction as everyone else, but they're going to get washed out because everyone else is so positive. So here we see a negative z product because our z-scores are inverses of each other, right? The variables are moving in the opposite direction. We had someone who's a short 2-year-old, but a tall adult. So once we have these z products, we just sum them. That's the numerator of our correlation coefficient formula, the sum of zx times zy. We sum them. Here we get 4.5. Right? We add all these up. Make sure you keep this guy negative because that matters. Then we take the sum of our z products, 4.5, divided by, sorry, this is the cell gets cut off a little bit, divided by n minus 1, right? So we have 7 participants. So that would be 4.5 divided by 6. And 4.5 divided by 6 gives us a correlation coefficient of 0.75. So all we did is add up our z products to 4.50. We took the sum of our z products and we divided by n minus 1, where n equals the number of participants. So 4.5 divided by 6 gives me a very strong positive correlation coefficient of 0.75, which tells me that we have a positive relationship between height at age 2 and adult height, meaning if you're short at age 2, you're likely to also be short as an adult. If you're tall at age 2, you are likely to be tall as an adult. Remember, these are still association claims. We can't say that height at age 2 causes adult height, but they are strongly related to one another. Now, we have this correlation of 0.75. We would call that a strong correlation, but we still need to determine statistical significance. We still need to know whether we should reject or fail to reject the null. We cannot just take this value on its own at face value. We have to compare it to a critical value table. So we want to write down and circle positive 0.75 because we're going to need it here in a minute. We need to know, is this extreme enough? Is it strong enough for us to reject the null? We have, just like we did for chi-square and just like we did for single sample t-tests, we have a critical value table for correlation coefficients. We can see it here. We need a couple pieces of information. We need n, which is the number of participants. Beware, this is not n minus 1 like the formula. This is just n. And then we need our alpha value. We're typically going to use either 0.05 or 0.01. So let's just assume an alpha of 0.05. Step 1 is to find the column we need. So we need 1, 2, 3. Oh, I'm sorry. I was doing 0.01. I said 0.05. So we need the first column. My bad. We're going to be working out of this column. So we know our critical value is somewhere here. And the second piece of information we need is our sample size, N. If you remember, our N was 7. So if we cross our N of 7 with our alpha of 0.05, we end up with a critical value of 0.67. That's our benchmark. That's our line in the sand. That's our hurdle. If our calculated correlation coefficient is greater than this benchmark, then we reject the null and we conclude that the variables are related to one another. If our correlation coefficient is less than this alpha, then we conclude that our variables are not related and we fail to reject the null. Now, one thing that we want to keep in mind, like all of our critical value tables, there's no negative numbers here, right? It's only positive numbers. So what we're really working with is the absolute value of our critical value, right? So we happen to be statistically significant, right? Our R is 0.75, which means we have a statistically significant positive correlation. We reject the null and we conclude that height at age 2 is related to height as an adult. But we would also reject the null if we had a negative 0.75, right? Because that would tell us that there's a significant inverse correlation. We want the absolute value of our R to be greater than our critical value. And that allows us to reject and fail to reject the null on both positive and negative correlations. So we're really focused on absolute value here. We can sort of ignore our negative signs in this situation. So our critical R is 0.67. Our observed R is 0.75. We reject the null and conclude that height at age 2 and adult height are positively correlated. Wonderful. Now we need to communicate this information to other people. So we need an APA-style conclusion. I'll read it here in full length, and then we'll break down its pieces and parts. A bivariate correlation was conducted to assess whether height at age 2 and adult height are associated with each other. We reject the null and conclude the variables are positively correlated with each other. R, degrees of freedom of 6, that's our n-1, equals our observed R value of 0.75. P is less than our alpha of 0.05. People who are tall when they are 2 years old are more likely to be tall when they are adults, right? Some take-home message. So the first thing we do is introduce the statistics and the research question. A bivariate correlation, that's our stat, was conducted to assess whether height at age 2 and adult height are associated. That's our research question. Next, we state whether we failed to reject or rejected the null. We were statistically significant, so we reject the null. We conclude that we have a positive correlation between these two variables. We provide our statistical statement, R, which is our test statistic, our correlation coefficient. And in parentheses, we put n-1, or as we've called it, our degrees of freedom. So R, degrees of freedom, equals our observed R, the calculated R, and P was less than alpha. Don't forget, if we are not significant, then we don't say P is less than alpha. We say NS instead. And lastly, the take-home message, explain it to a 10-year-old. People that are tall when they're 2 years old are more likely to be tall when they are adults. Clean, easy, simple. Okay. I want all of you to take this example, click pause on the video, and then see if you can do this by hand all the way out by yourself, all the way to an APA-style conclusion. Take your time, go back and look at the static PowerPoint slides that we've already gone over, and see if you can reach the appropriate both R coefficient and the APA-style conclusion. Our research question here is about the correlation between memory and SAT score. We're going to assume an alpha of 0.01. I've given you 5 participants, each with a memory score and an SAT score. I've given you the mean and standard deviation for both memory scores and SAT scores. You're going to find the Z-score for all 5 people for memory. You're going to find the Z-score for all 5 people for SAT. You're going to multiply those Z-scores to find a Z product. You're going to sum them. Then you're going to divide by n minus 1, so 5 minus 1, to get our R coefficient. Go ahead and press pause. See if you can do that. Remember, round to 2 decimal points for every calculation. So I'm going to go silent for a second, and then I'll pick back up with the lecture. So press pause, do the math, write your APA-style conclusion, and then press play to check your answers. Okay, I'm back. Hopefully you have completed the practice problem. Let's just take a look at the results. So I'm going to leave this up for a minute so that you can check your math and see if you got it correct or perhaps somewhere where you went wrong. These are our Z-scores for variable 1. We can see person number 1 is right on the mean, right? So they have a Z-score of 0. Person number 2 for memory score is slightly below the mean. Person number 3 is even more below the mean. Person number 4 is above the mean. And person number 5 is also above the mean. So take a second, look at your answers. Notice that we have a correlation coefficient that is very close to 0, 0.03. So that correlation coefficient of 0.03 is not very promising. Remember, we talked about that the absolute value of correlations determines their strength, right? The closer they are to 0, the weaker they are. The further away they are from 0, the stronger they are. Here we have something that's almost exactly 0. So what this should already indicate to us is that we have a very weak, probably 0 correlation. We're probably going to end up concluding that these variables are not related to one another. I'll give you another minute to maybe check your math and highlight any areas where you might have gone astray. Okay, so let's move forward with our R of 0.03. Our next step, we sort of write down, circle this R of 0.03. We want to compare it to our critical value. Oops, sorry, here I see a little mistake. In the practice problem, we said alpha is 0.01. And here, unfortunately, on my slide, it says 0.05. So when we click through here, it's I did the correct thing. So sorry about that. Sorry, this is 0.05. I'll fix that for the static slides. We need 2 pieces of information. We need our alpha, which, again, sorry for my mistake, is 0.01. And then we need our sample size, our n, which is 5. And so we can see that to be statistically significant, we would need a very large R coefficient, right? 0.93 or beyond, or negative 0.93 or beyond. We're going to compare that to our observed R value of 0.03. And so we're going to find that we fail to reject the null. We are not statistically significant, right? We did not get beyond our hurdle or our line in the sand. And we conclude that memory and SAT score are not correlated with one another. There's no relationship between your memory and your SAT score. That's what we found. So our APA style conclusion looks like this. A bivariate correlation was conducted to assess whether memory scores and SAT scores are associated with each other. We fail to reject the null and conclude the variables are not correlated. R degrees of freedom equals 4, equals 0.03, not significant. A person's memory score is not related to their SAT score. Okay, there are some more practice problems at the end with all of the answers worked out, as we just saw from our last two examples. We're going to transition quickly to a few slides of discussing how we interrogate statistical validity now that we know about the statistics. If you remember from part 2, we kind of skipped over this a little bit, but now we're really going to take a look. When you get to the end of this lecture, I highly recommend completing those practice problems and checking all of your answers so that you're sort of comfortable moving forward and being able to do this on an exam. But for right now, to finish this lecture, we are going to discuss statistical validity, or how can we tell how well the data support our conclusions. So we already just sort of went over how do we tell that a correlation is statistically significant. We use this R table to give us our critical value, and then we judge whether our observed R is large enough, is larger than the critical value, or is more extreme than the critical value. When you see this in journal articles, this is a very common way of representing correlations in a correlation matrix or a table, such that correlations are listed by sort of crossed with different variables. So we can see the correlation between happiness, for example, and the amount of time that you spend alone, right? Or happiness and the amount of time you talk to others, or happiness and the correlation with the amount of small talk that you engage in. So here we have just like a bunch of correlations. And when you're reading a journal article in an academic publication, you will typically see asterisks next to the significant correlations. If we come all the way down here to the bottom, the footnote of this table, we see that a single asterisk means that something was significant at 0.05. If we have two asterisks, it means something was significant at 0.01. So you'll often see these represented like this. We can tell the distinction between our negative and our positive correlations, and then we can tell whether they were significant at 0.05 or were significant at 0.01. Now, obviously, if something is significant at 0.01, we consider that better evidence, right? It's a stronger correlation. Let's look at the correlation between happiness and small talk percentage of conversations. That's negative 0.35. So that's a moderate negative correlation. That's a stronger correlation than the correlation between happiness and the amount of time spent alone, negative 0.27. Even though they are both significant, this negative 0.35 we might consider to be better evidence or stronger evidence, right? Not all evidence is created equally. Just because something is statistically significant doesn't mean we treat it equally as all other statistically significant results. We can compare these two, and we can say that the relationship between happiness and small talk is a stronger relationship than happiness and being alone, even though they are both statistically significant. Next, we need to look at our scatter plots to assess the effect of outliers. So I want you to look at our top two scatter plots here, both of our A's, and try and identify the outliers in those scatter plots. The name outlier sort of gives you a hint as to what you should be looking for. You should be looking for a data point that falls out of the normal pattern, right? It lies outside of the normal pattern. So we're looking at these two data points. And let's illustrate for a second the effect of outliers on our correlation conclusions. If we were to describe the relationships of our top two scatter plots, they would be maybe small to moderate positive correlations, right? They would look like this, these blue lines for our lines of best fit. These are positive-ish correlations, maybe small to moderate. If we remove those single data points, right, going down to our B scatter plots, just by removing a single data point that is an outlier, we end up with a completely different relationship, right? A completely different slope of our line of best fit, such that if we were to look at the scatter plots for our two Bs, then we would say there's no relationship. This is a zero correlation, right? Nothing's going on here. Our line of best fit is straight across. There's no relationship between our two variables on our y and x axes. But the addition of a single outlier in each of the cases above changes our perception of that relationship. That's dangerous, right? We don't want to be making broad scientific conclusions based upon a single data point. That one individual who was captured is our Michael Jordan, right? It's our person that makes everyone else look different. And we might not want to base our conclusions on this single individual rather than all of these individuals who are showing a different pattern. So we're not going to talk about, I think as I mentioned previously, we're not going to talk about how we deal with those. That's a little bit beyond the statistics of this class. What we want to understand is that they can have an untoward effect, an unwanted effect, and we need to be careful that we're not basing our conclusions simply on those outliers, which is why we always like to visualize correlational research. Another point about interrogating association claims is the statistical validity of association claims, is restriction of range. Here we're looking at SAT scores on the x-axis and GPA from college on the y-axis, right? Does your SAT score from high school, is it related to your GPA from college? And it looks here like it is, right? We have probably a moderate positive correlation. If we drew a line of best fit, it'd go right here. But notice that we're only looking at SAT scores of 1200 or above. Maybe these data are from a really elite private school that's very selective, that requires an entrance exam. And so only the people who excel at this entrance exam are allowed into this high school. And then when they take the SAT, they all do really well, right? 1200 is a pretty good SAT score. And obviously anything above 1200 is becoming a very good SAT score. 1600 is perfect. So what we have here are a sample of odd students, right? These are overachieving students, maybe from a very elite private school that's very selective. And so we see this positive relationship with them. But if we were to include others who score below a 1200, it might change the nature of the relationship, right? So if we restrict our range to only people above 1200, we see a positive relationship, a moderate positive relationship. If we then expand our range on the SAT score to the full range, then we look like zero correlation. We look like nothing, right? Nothing is going on here. So the restriction of our range completely changes our conclusions about this relationship between GPA in college and high school SAT score. So we have to be careful. This restriction of range can happen based on the measurement tool that we're using. Restriction of range can happen based upon our sampling methods is probably maybe the most common form of restriction of range. We only sampled on the left this super elite private school. Maybe on the right, we sampled, all the public schools, all of the schools, whether they're public or private in a certain area. And so we get maybe a more representative sample over here on the right, and on the left, a less representative sample. That's a possible way where we could see restriction of range. Another issue in interrogating statistical validity of correlations is curvilinear associations, or maybe exponential or nonlinear associations. Here we have on our x-axis age and our y-axis use of the healthcare system. And we want to know, is age related to how much you use healthcare? And if we were to calculate a correlation coefficient for these data, our line of best fit and our correlation coefficient would be very close to 0. We'd have a horizontal line of best fit if we found the line that best fits these data, that reduces the distance from the data points. So if we just looked at the numbers, we would say age and use of the healthcare system are unrelated to each other. There is no relationship between age and use of the healthcare system. Clearly, that's not true. Clearly, there is a relationship. It's just a non-linear relationship. It is curvilinear. In this case, it's U-shaped, such that early in life, we use a lot of the healthcare system, and late in life, we use a lot of the healthcare system. But in between, we use very low amounts of the healthcare system. So we end up with a curvilinear U-shaped relationship. Now, there are other curvilinear relationships, or exponential is a curvilinear relationship. For example, we can have an inverted U curvilinear relationship where we're low on the ends and high in the middle. But the point here is that in such relationships that are nonlinear, correlations don't do us any good. They are not a good tool for assessing those relationships between two variables that are curvilinear. We're not going to get into what to do about that. We're not going to get into what other statistics allow us to assess curvilinear relationships. That is beyond the scope of this class. Again, just know that bivariate correlations are unable to assess these curvilinear or nonlinear associations. Okay. That's it for part 3. You've got a few different practice problems that you can go through here with answers and sort of a walkthrough of each. I highly recommend that you do these and take them seriously, practice them, drill them, make sure that you can end up with the correct R as well as the correct APA style conclusion, and be prepared for the exam. Thanks, everybody. Again, watch this video as many times as you need. Watch it with the static PowerPoints. I think that that's often helpful. Feel free to pause the video at any point, rewind, fast forward if you feel like you missed something. But make sure you're getting your money's worth out of looking at this video, because this is a bit different from the things we've been encountering in the past. And you might need to sort of repeatedly take a look at this in order to master it. So make sure you're comfortable with these concepts. Make sure you're comfortable with the math. Do these practice problems. And as always, let me know if you have any questions.